Okay, this is introduction to batteries. Pause it and have a look so you can skip through to the slides that you're interested in. So pause now. Okay, pause it for this one. If you don't know how coal-fired power stations work, there's a video on this YouTube channel you can have a look at. The reason that we're interested in batteries is there's a few reasons. I've already talked about this, that we need some sort of energy, chemical energy, that's easy to transport, move around for our trucks and cars and everything. So at the moment we used carbon-based chemicals to contain the chemical energy, and they have a lot of energy in them. The problem is obviously when you react them with oxygen, you're making carbon dioxide, which is warming the earth. Batteries with metals in them also have energy as a portable means of energy, and they don't produce carbon dioxide when they're reacting. So electricity, not just portable energy, but producing large amounts of electricity. At the moment, lots of countries around the world use coal and use our coal too to produce electricity. Obviously, if you combust it, you're making carbon dioxide. There's other ways of producing electricity other than burning coal. If you don't know how a coal-fired power station works, ask me. No, that was in the previous slide. Okay, so you can use solar panels, hydro with water, or wind turbines. The problem with producing electricity this way is that sun and wind aren't out, at night or when it's calm. So we have to store the energy when it's produced. So batteries are a way of storing electrical energy as chemical energy. So instead of using carbon-based fuels like coal or petrol to get our energy from, we can trap energy in metals. And the main difference with, well, there's an example on YouTube where they're trying to use magnesium as their form of energy. Carbon dioxide is a gas, magnesium oxide is a solid, so you're not releasing stuff into the air. The oxidation numbers, they're both being oxidized. So oxidation number is 4, going from 0, both of them going from 0 to 4 plus or to 2 plus. Okay, so South Australia seems to be ahead of the rest of us in producing electricity in means other than coal-fired power stations. So they've got all of these wind and sun turbines, and they have had a problem. They had a big storm and a lot of these got knocked over, and so their electricity grid was knocked out. So they realized that they needed to store it and back it up. So the Tesla, you may have heard Tesla, Elon Musk put in these this bank of batteries to store their electricity. Okay, apart from producing carbon dioxide, there's millions of reasons why coal is a bad way of producing our electricity. The energy in the coal is not a very efficient process when it's converted into electricity. A lot of the energy is lost as heat, and quite a few lots of processes will lose energy to varying extents as heat. So it would be better to turn the chemical energy directly into electricity rather than reacting it with oxygen and making carbon dioxide and getting heat, which is eventually turned into electricity. So batteries have got lots of good things about them. You can store energy in it. You don't waste energy as heat. You can transport move them around, and they don't produce carbon dioxide. Okay, so we're up to our notes. So batteries, we're going to look at two sorts when batteries are working normally. So these words, spontaneous, meaning it's a natural reaction, it wants to happen spontaneously. You need to connect that with the word galvanic, so they're the same idea. This is when chemical energy is naturally, we're going to turn it into electrical energy in a battery. So there's three sorts of galvanic cells. We're doing primary and secondary batteries at the moment. The difference between a cell and a battery is what we're looking at in class is a cell where there's one anode, one cathode. The electrons are being lost directly. But if you have a whole lot of cells together, then that's a battery. So we're using primary cells, which you can't recharge, and secondary cells, which you can, and then we'll look at fuel cells in another video. So these are all galvanic. They all turn chemical energy into electrical energy. This one here, we're going to use, when we recharge it, it's not spontaneous, and we'll use the word electrolytic. Okay, so another word to add to our galvanic spontaneous is discharging. All of these words are interchangeable. So discharging is when a battery is spontaneously reacting. It's got two parts in a battery. The chemicals which are going to lose the electrons, so the anode end, which is the negative end on the battery. So electrons, this is a really bad wire coming out of here. Electrons come out, energy is lost through whatever you're charging using your battery to make work, and then they come back in here. So the whole thing is losing electrons. They don't kind of lose it just as they're going through there, but energy is the whole sort of process. Okay, so naturally the other end, the positive end, is the cathode in the other picture. So recharging is when your battery's flat and we need to put the electrons that were lost from the chemical in here back into this end. So you need some sort of power supply. Naturally it's working as the battery used to be working, so the electrons come out of the negative side of this, and you can't rub that negative off the battery. So in this case, the polarity on the battery has swapped. So when it's being recharged, electrons are being added. This is the reduction reaction. This is the cathode now. So for recharging, the cathode is negative. For discharging, the cathode is negative. The anode is negative. Okay, so we'll look at a little table and put those together. So the reason is we can't really rub that off. So here's our words together: galvanic, discharging, spontaneous reaction when your battery's working as it should. So electrons are being lost from something here to something that's more electrolytic. Electronegative wants electrons more. So the copper would like the electrons more than the zinc here. So this loses them. So this is our setup of a battery. So there will be some chemical in there that is gaining and some chemical in there that's losing. So when you want to recharge your battery, you have to use some sort of power supply to force the electrons back onto here to recharge it. So electrolysis is recharging, it's forcing energy back and electrons back onto something that wouldn't want them normally. So it's a non-spontaneous reaction. Okay, so we need to set this table up. Hopefully getting used to these words. I should have galvanic in this list too, and I should have electrolytic in this list. So basically, if you remember this one, you can work out all the others from it. So when your battery is working, the negative end is where the electrons are coming from. The negative end is where oxidation is happening. It's the anode. So this is the negative end of the battery, normally written on it. And so therefore the other end is where the electrons are going. sorry, other end down here, is where the electrons are going to. It's the cathode. It's undergoing reduction. So this is a normal battery. So when you recharge it, the negative end, you can't rub that off. So this time you're forcing electrons back into this end, so it's undergoing reduction. So you might have noticed, actually I should have mentioned, here when it's recharging, you put the negative end of whatever you're using as your power supply with the negative end of the battery. So if this was a car and it was flat and you had to get somebody else's car to recharge your battery because it had gone flat, you'd have to put the negative end of their battery with the negative end of your battery in the car. So it's negative to negative, positive to positive when you're recharging. Okay, all our batteries they're basically the same setup as what we do with our beakers. So our salt bridge we call an electrolyte in the battery. So the reason that we have a salt bridge or an electrolyte is that you're moving negative electrons from one side to the other, so the charge is being unbalanced, so you have to balance the charge. So your electrolyte or salt bridge have to have ions, they have to have charged particles which are free to move. And when they move, they can't react with anything else in the new situation and make a precipitate, so they can't come out of solution or just react with other chemicals generally. They're positive charged particles, so the positive ones move towards the cathode. The cathode is where reduction's happening. This is where the negative electrons are being added. So to balance that build-up of negative electrons, we have to have our positive ions moving in that direction, and the opposite for the anode. So parts of a battery. In all of the batteries, you need to identify which direction the electrons are moving. That's the main thing, and quite often the easiest way of doing that is to find where the negative is written. The negative is the anode, that's where oxidation is happening. That's where the electrons are coming from. Cathode, the positive electrode, is where they're going to. That's a place of reduction. So the negative and the positive help you generally. And we also need to identify which ions there are in the electrolyte and which direction they're moving. So primary cells, these are batteries that can't be recharged. So you use them and then you throw them away. The reason that they can't be recharged is that the products, what you make, move away from the electrodes. So if the chemical has lost electrons and turned into some product that's lost its electrons, you can't add the electrons back to it if it's moved away from the electrodes, so you can't recharge it. So our first example is a zinc carbon dry cell. Is it dry? No, it can't really be dry because you have to have some way for the ions in the electrolyte to move. So there has to be a liquid of some sort. Generally the liquid's water that we're looking at, but you can have batteries that don't have water as the liquid. So they have some sort of paste because it's really concentrated. There's very little water or liquid particle in there, but there's enough to make the ions move. So this dry cell, first thing we need to look at whenever you're looking, where are the electrons coming from and where are they going to? So you can see down here, this is the anode, and the anode's made of zinc. So our batteries have a metal in them because metals can lose electrons. So in this case, the zinc is the metal that's going to lose the electrons. And you can see the entire outside of the battery is made of zinc. So electrons are lost from this zinc and they go around, sorry about the wonky thing, they go around, they go down to the cathode, this is the cathode positive, go down this middle bit and they're given to a paste in here. Alright, so we know that zinc is losing the electrons, undergoing oxidation. So what's gaining the electrons is quite complex. We've got our manganese dioxide here, dimanganese trioxide there. We've got a very strange, this is a complex half equation, but instead of balancing your oxygen with instead of balancing hydrogen ions with hydrogen, you're balancing them with ammonium. So we've got manganese dioxide and ammonium ions in here. Ammonium chloride, the chloride's a spectator ion, it's not doing anything. And it's getting the electrons, all of that is getting the electrons to turn into this. So the electrolyte, all these ions are floating around, your ammonium and your zinc. See if you can pause it at the moment and think which direction would the ammonium and the zinc, sorry, travel? Well, okay, hopefully you paused it because they're going in this direction. So the electrons, negative electrons are coming here. This is the cathode, negative electrons. So you want the cations to move across to the cathode. You've also chlorine ions floating around, so you need some negative ions in here, either being produced or already in here, and they can go across because there's been a loss of negative ions with the zinc. There's a problem with this. The outside of the battery is actually one of the reactants, and it could erode away. Okay, so you can look at that. Can you do this? So could you balance this if it had just a plain acid electrolyte? So just a normal complex half equation. Can you pause the video, see if you can balance it? Okay, I'll show you what to do. First thing, you must make sure that you've got the right number of manganese ions. So everything other than oxygen, make sure you balance that. Then we have to balance the oxygen by adding water. We've got 4 oxygens on this side, 2 lots of 2. We've only got 3 on this side, so we need some extra oxygens over here. You've now added 2 hydrogens, so you have to put hydrogen ions, and you can balance. There's no charge over here, but there's 2 plus charge, so you need to cancel that out by adding 2 negatives. Okay, alkaline battery, which looks kind of similar to the previous battery. In this case, though, we have got the zinc, which was losing its electrons on the inside. So this whole thing up the middle here is now the anode. And it's got a alkaline electrolyte, which is OH, hydroxide is alkaline solution. So this half equation you could just do. It's still the zinc losing the electrons. The zinc's on the inside, not on the outside, but still the zinc losing the electrons. So you could write this half equation with just the zinc ions and the electrons. But you can write it with the zinc, the hydroxide ions move across. Because this is losing negatives, this is the anode, oxidation's happening here, anode, anions will move across, and the zinc ions that are formed will form zinc hydroxide. So I could write zinc hydroxide as well, and it's a solid, so it would sit on here. Actually, it mustn't be a solid because these are not rechargeable. Okay, so it goes from the anode in the middle all the way around, so the cathode is on the outside. So this time we have a similar, same chemicals as previously, except instead of doing our complex half equation and balancing it with acid or ammonium ions, we have an hydroxide electrolyte. So on the next slide I'll show you how to balance this hydroxide electrolyte. But first of all, let's make sure we know which way. So this is the anode. We're losing electrons, I said before, so the hydroxide ions move across to balance them. Anions, anode. We've got some potassium positive ions here, so and some zinc that's being produced. Don't forget about what's being produced. So in some exam questions, I have seen exam questions where what's being produced is you're expected to know that it moves across as well. Okay, so how to balance a complex half equation with hydroxide ions rather than hydrogen ions. You can just balance it straight away because you've got hydroxide ions and water, so you can just work out which side to put each of them on so that it's all balanced. Last year students were finding this difficult, so I think I'll explain how the textbook does it, and you might find it easier. Just remember that the textbook is a fake way of doing it because you don't have hydrogen ions. It's just that we've learnt the method with hydrogen ions, so it might be easier to remember. Alright, so you balance the reduction half equation as if it was had hydrogen ions. So hopefully everyone's okay. You start with manganese here. You've got 2 on this side and you didn't have 2, so you had to put a big 2 here to start with, which means you've got 4 oxygens on this side and only 3 on that side. You have to put an oxygen on that side in the water. And by doing that, you've got 2 hydrogens. Put the 2 hydrogens on this side. Don't forget the plus. So you've got 2 positives, no charge, so you have to add 2 negatives. So hopefully everyone's all right with that. So once you've done that, then we need to get rid of these because it can't have an acid and a base at the same time. It doesn't make any sense. So this is just a method of working out how to balance it with hydroxide ions. So we need to get rid of all of these. So we add hydroxide ions to both sides until we get rid of all of these, and we turn what we've added. If you put a hydrogen ion onto that, you've made a water molecule. So we've got 2 of these, so we're going to need 2 hydroxide ions to make 2 water molecules. So because you put 2 on that side, you have to add 2 hydroxide ions onto the other side. So we'll put these both together now and make our 2 water molecules. So you've got water on both sides, so you're going to have to cancel out some of the water. So you've got 2 on this side, 1 on that side. So you get rid of a 1 water molecule from each so that you've got 1 water molecule left on this side. So you could just do this balancing straight away, but people do tend to get confused. So you would have got balanced this, so you've got 2 oxygen and 3 oxygen here, and then I find people, because they need 1 extra oxygen and they're used to just adding the water as the 1 extra, they put the water on this side to start with and then they don't know what to do. So this is an odd number, this is an even number. Hydroxide ions come with 1 of each. So if you add, so that's even. If you add the water to this side, you've got 1 oxygen and 2 hydrogen, so they're odd as well. So putting the odd ones, so you've got 1 odd, 3 oxygen here is odd, and 1 oxygen added compared with the hydrogen here is odd. So you've got odd on both sides and even on both sides so that they will cancel out. I'm not explaining that very well. Okay. So still with primary cells, we've got an overall equation here. You need to be able to break the overall equations up and look at them as separate equations. So what's gaining, what's losing? We've done zinc quite a few times, so you can see zinc is a metal here and it's an ion there. So clearly the zinc has lost the electrons, the zinc has undergone oxidation. This is a alkaline half cell. So you've got hydroxide ions floating around too. So our reduction half equation, you've got the silver turning into the silver metal, and if you could balance that with the hydrogen and then get rid of the hydrogens and turn it into hydroxide ions, and you'll end up getting this half equation. So you need to practice, see if you can do these if it's got a hydroxide electrolyte. So secondary cells. So these cells are called secondary cells because they can be recharged. So your rechargeable batteries that you buy, hopefully you've got them. If you're going to recharge them, you need a higher voltage than the voltage that the cell would produce to force the electrons back on. So you have to use a higher voltage. And in order for the cell to be able to be recharged, whatever you're producing, whatever you're stealing the electrons from and the product that you make, it has to stay in contact with the electrode so that you can add the electrons back. And the same for the thing that you added the electrons to. You have to be able to remove them. So these batteries have, so we're going to do lead acid. These are the batteries that you find in your car. So they've got lead in them, Pb, and lead's in 3 oxidative states. So we've got pure lead metal, which is oxidation number of 0, lead ions as lead sulfate, so same as the charge on the ion, so 2+, and we've got lead oxide ions, so we've got an ion that is a 4+ charge. They have an acid electrolyte, so we're going to do our complex half equations with hydrogen. Okay, so we've got lead forming lead sulfate, and so we start with lead and we form lead sulfate, and we start with lead oxide and we form lead sulfate. So the two, this is the oxidation half equation, this is the reduction half equation. The two reactions both end up producing the same coating, lead sulfate, on the electrodes. So these individual things here are cells. This electrode is the negative electrode. This is the anode where oxidation happens. So all the electrons are coming out of here. So they come out of, this is one this is one cell, an anode and a cathode. This is another cell, an anode and a cathode, another cell. So there's actually 6 cells in a battery. So that's the difference between cells and batteries. So when we set them up in the lab with our beakers, we only are making a cell, not a battery. Okay, so the orange ones are all made of lead. So that's where the electron's going to be lost from. They're the anode. And when we lose the electrons, we're going to make lead 2+ ions, and there's sulfate in the electrolyte, so it's going to make lead sulfate paste. Okay, so it oxidizes. So therefore it goes out of the anode here, out through the car to charge your, make your car work to start with, to give it a spark. Okay, so the lead oxide on the plates is 4+, oh, +4 I should say, oxidation number. So it's gone from +4 down to +2, made lead sulfate, just like this one. And it's been reduced. So we've got our electrolyte, hydrogen ions, and our sulfate, which is going to become lead sulfate. So the hydrogen ions are moving to balance the charge. This is a cell, which it's only got the 2 electrode. So I'm just showing you one of these. So the anode and the cathode from here, just one cell. So this one's losing the electrons. That one's gaining the electrons. This one is therefore the anode. It's negative polarity. Oxidation's happening here. Electrons being lost. We're going to make lead sulfate. So we need the lead and the sulfate. The lead loses the electrons, and then the sulfate can join with it to make lead sulfate. Okay, so the sulfate has to go across here to join with the lead 2+ that was produced. On the other side, the electrons are being added. We're forming, these are 4+. This is lead oxide, this is 4+. It gains the electrons and becomes 2+ as well. So the sulfate is also moving in this direction to make lead sulfate. Over here, the oxygen that was on part of this, it is joining, it's getting the electrons and joining with the hydrogen to make water. So the negative electrons that are moving, because this is going both ways, it's not really balancing the charge. The negative electrons that are moving across here have to be balanced, so the hydrogen ions moving in this direction balances the charge. That's the electrolyte, why you have an acid electrolyte. So if we recharged, if we wanted to write a recharge whole equation, we can do our discharge half equations. So our lead losing, getting the sulfate, becoming lead sulfate, lead oxide, getting the electrons and the sulfate to become lead sulfate, and the electrons being added to this to become water. We can put them together, do an overall equation. So if we want to do the recharge equation, it's just this in reverse. So the lead sulfate, the electrons will be given back to the Pb2+ at the anode, because it will now be the cathode, and you'll make lead again. So we're doing this in reverse. So if you do the discharge equation, all you have to do is pick the whole thing up, turn it around, and that's the recharge equation. So you started with lead on both plates, and then you end up with lead metal on one plate and lead dioxide on the other plate. What happens to the pH when lead acid battery is discharged? So underline these, discharge, pH. So we know the pH is the concentration of hydrogen ions or hydronium ions. So when it's an acid, then the concentration of hydronium ions is going up. So when it's being discharged, the lead and the lead oxide are using hydrogen ions. You're using them up and turning them into water. So you're removing hydrogen ions. Concentration of this has gone down. It's become less acidic. So the pH goes up. Just remember this, don't get tricked. You're decreasing the concentration, so it's moving more in the basic direction, that direction. So you're increasing the pH, increasing. At which electrode does the pH change? So the hydrogen ions were used for this half equation. This is where the electrons are being gained. Reductions happening there, reductions happening at the cathode. What was the potential difference of the lead acid battery? So how many potential difference? What's the voltage that you can produce? So there are 6 cells, and each cell has 2 volts. So if you've got 6 cells that each produce 2 volts, then a car battery is a 12-volt battery. So the potential difference that you would need to recharge it is 14 volts, which if you ever have to recharge someone's battery, apparently in modern cars you can't really jump start someone's battery. It's not very good. I'm not sure why, but with old cars, if you're going to jump start someone's battery because they had a flat battery, you had to have your car running so that your car was producing more energy, so that otherwise the battery on the car that was being used to recharge the other battery would go flat really quickly. Okay, the reaction below represents the discharge cycle of a standard lead acid rechargeable battery. So discharge, a spontaneous reaction, galvanic cell or cells working normally. So during the recharge cycle, when you're charging the battery, it's electrolytic, you're forcing something to happen that is not spontaneous. On the electrochemical series, discharge would be in this sort of orientation, but a recharge would be, because you've made the products, a recharge would be in this sort of pattern. Okay, so during the recharge cycle, the pH, so this is discharge, you're using these, pH, concentration of hydronium ions has gone down, pH goes up. So in recharge, you're doing the opposite. You're making more of these, concentration of hydrogen ions goes up, so the pH goes down. So the pH decreases, and for recharge, you need to add electrical energy to recharge your battery. So you need to plug it in. So D. Okay. How long do batteries last for, and what sort of conditions help them work? So pause and have a look at page 145, take your own notes. So just pause it at the moment. Okay, so the battery life. Every time you discharge and recharge a cycle, you're wanting it for it to be rechargeable. The products have to stay stuck onto the electrode. So some of them will disattach, come off the electrode, and also other reactions can happen. Different sort of side reactions can happen. So you're not having the same products. So after a while, you can't recharge the battery anymore. And while this is all happening, the voltage that you're getting produced may start to decrease. So everything speeds up when it's hot, and that's including all the side reactions. So if you have your battery too hot, then you can speed up all the different side reactions and the battery won't work very well anymore. If everything's too cold, everything slows down and the electron loss slows, so the voltage that you get from the battery would decrease. I should have added that. Okay, lithium metal makes lithium ions, lithium metal and lithium ions. That's one of the classic sort of batteries. So which sort of conditions would you expect to get the largest number of discharge-recharge cycles? So pause it, answer it. Okay, so you want it cool. It works best when it's cool, but this is frozen, and you've got a paste which could become solid, so that's too low. This is the best. Okay, I think that's it.